Now, in this video, we're going to look at how to draw the Lewis structure of dinitrogen pentoxide. Now, so the first thing that we would have to do is to count all the valence shell electrons of the atoms forming the compound. Now, this compound contains 2 atoms of nitrogen and 5 atoms of oxygen. Now, nitrogen is in the group 15 on the periodic table, having 5 valence shell electrons. Oxygen is in group 16 on the periodic table, having 6 valence shell electrons. So we have a total of 40 valence shell electrons to be considered in drawing our Lewis structure. Now, in choosing our central atom, nitrogen and oxygen both find themselves in the second period on the periodic table, and in their valence shell can only have a maximum of 8 electrons. Nitrogen would require 3 electrons to get to 8 and complete its maximum number of electrons in its valence shell, and oxygen would require 2 electrons to get to 8 and complete the number of maximum electrons that makes up its valence shell electrons. So the atom, the central atom, is the one that is able to make more bonds. And in this situation, nitrogen will be considered more favorable as the central atom for this compound. And also to be taken note is that nitrogen has a lower electronegativity value as compared to oxygen. The electronegativity value of nitrogen is about 3.04, and that of oxygen is about 3.44. Oxygen with a higher electronegativity value tends to be a little greedy with its electrons and wouldn't like to share with other atoms. So the atom with a lower electronegativity value is considered to have a better tendency of sharing its electrons during bonding and would be considered a more favorable central atom of the molecule. So next we draw bond with the central atom. We have 7 atoms over here. So we can have a skeleton structure out of this. So considering nitrogen as our central atom, we can start with a skeleton structure, taking note that we have 40 electrons to work with. So we're going to keep 2 electrons between the atoms to form the chemical bonds. Then we go around the outside and fill the atoms until we satisfy their octet. Now that makes 14 electrons. So we'll be left with 26 electrons to go around and fill the atoms. So these are our 40 electrons. Now, this oxygen atom is satisfied. It has 8 electrons in its valence shell. And so these 4 oxygen atoms here have satisfied their octet and they are happy and satisfied. This particular oxygen atom here has 6 electrons around it. And in order to be happy, it should not have less or more than 8 electrons to satisfy its octet. And so because of that, this particular oxygen atom would not be happy, and the entire molecule structure would also not be stable. So this particular skeleton structure will not be a favorable one for dinitrogen pentoxide. We need to find a combination where all the atoms are satisfied. Now let's consider this skeleton structure of nitrogen pentoxide of 2 skeleton structures being fused together. So we would have a skeleton structure of this form. Which would have the appearance of oxygen as the central atom, with the oxygen coming in between the nitrogen atoms, making an exception to the rule that the least electronegative atom is placed as the center. So in choosing the skeleton structure,
we're looking at the octet rule consideration and the overall stability of the molecule. So it makes the Lewis structure of dinitrogen pentoxide rather quite tricky and challenging. So now we have 12 electrons making up the chemical bonds. And so if we are working with 40 electrons, we have 28 more electrons to fill the atoms until we satisfy their octet. So let's go ahead and distribute 28 electrons. So we have all the 40 electrons distributed, but is nitrogen satisfied? Nitrogen has 6 electrons. This nitrogen also has 6 electrons, 2 in each bond around the nitrogen atom. So nitrogen is not satisfied. So we need to convert this lone pair into a bond. So let's convert this lone pair into a bond and this lone pair into a bond. So we're going to have so now this oxygen has 8 electrons, nitrogen has 8 electrons, this also has 8 electrons around it, and so now with this structure, each atom is satisfied, and each has 8 electrons in their valence shell. Now to establish whether this molecule is stable, let's determine the formal charge on each atom. And for the formal charge, we'll be guided by the formula. Where V subscript E is the number of valence shell electrons of the atom minus the non-bonding electrons of the atom, then minus half the bonding electrons of that reference atom. Now, if we are to consider this atom, oxygen has 6 valence shell electrons. 4 of them are not involved in the bonding. So the non-bonding electrons of this particular oxygen atoms is 4. 4 electrons over here are involved in bonding. So the charge on this particular oxygen atom is 0. It is the same arrangement on this oxygen atom, which should also have a formal charge of 0. With this particular oxygen atom and this one, the valence shell electrons is 6, the non-bonding electrons are 6, and the bonding electrons is only 2. So this oxygen atom has a formal charge of -1, and with the same arrangement, -1 formal charge on it. Now with this nitrogen, formal charge of nitrogen is 5. All the electrons of nitrogen are involved in bonding, and so nitrogen does not have a non-bonding electron. And we have 8 bonding electrons, 4 here, 2 here, and 2 here. So nitrogen has a formal charge of +1 on it. Is the same arrangement of this nitrogen. With this oxygen atom, the valence electrons is 6, the non-bonding electrons are 4, then the bonding electrons are also 4. We have 2 here and 2 here. So the formal charge on this oxygen atom is 0. So the algebraic sum of all the total charges of the atoms here is 0, making this Lewis structure for dinitrogen pentoxide a favorably stable one. Now, without compromising on the octet rule regarding each of the atoms within this molecule, we could consider some possible potential Lewis structures of dinitrogen pentoxide. For example, if lone pairs are converted into bonds, or vice versa, bonds are converted into lone pairs, as in this example, then resonance structures of dinitrogen pentoxide could be generated. So we could have
In this structure, when a lone pair converts into a bond or a bond converts into a lone pair, we're going to have this resonance structure with the former charges on each atom when calculated as and when this lone pair is converted to a bond, or this bond is converted to a lone pair, we could have this resonance structure. And the former charges of the atoms for this structure can also be calculated. And the effective former charge on the molecule will be 0 because plus 2 minus 2 is 0. We could also have and the former charge for each atom can be calculated, and we could have and the algebraic sum of the former charges is 0 here. So we could have potential Lewis structures for dinitrogen pentoxide. So for this structure, each of the atoms within the molecule are satisfied because they satisfy the octet, and that makes this structure of dinitrogen pentoxide a stable structure. This is also a stable structure. This is a stable structure, and this one is also a stable structure. So we could have possible potential Lewis structures, which will be recognized as favorable Lewis structures for dinitrogen pentoxide. So that is the end of my video. Thank you very much for watching, but keep watching.